Welcome to The Explainer. Today, we're going to dig into one of the greatest challenges in aviation history: how in the world engineers figured out how to fly faster than the speed of sound.
So, have you ever looked at a modern jet fighter and a classic propeller plane and just wondered, why are they shaped so differently? One is all sharp and pointy, the other is kind of rounded and blunt. And trust me, it's not just about looking cool.
It all comes down to how air itself starts to act when you get really, really fast. As you start pushing up against the speed of sound, the rules of physics literally change, and the shape of the airplane has to change right along with them. All right, let's get into the first big secret here. You see, at low speeds, air is pretty chill. It acts like an incompressible fluid. But as you approach the speed of sound, that all goes out the window. Air becomes compressible. And that, right there, is where everything changes. Think of it like this, okay? When a plane is flying slowly, subsonically, it's sending out pressure waves ahead of it, kind of like the ripples from a boat. Those waves warn the air in front, hey, we're coming through, and the air has time to part smoothly. But once you go supersonic, bam, you're outrunning your own warning. The plane just slams into the air with zero notice. And you can see exactly what happens right here. On the left, you've got those nice, smooth streamlines of slow flight. But look to the right. Once you pass Mach 1, it's a totally different story. The air molecules just can't get out of the way fast enough, so they stack up, pile up, and create this wall, this super dense barrier that we call a shock wave. And this invisible wall is really the villain of our story. This shockwave is what created the infamous sound barrier that early pilots thought was, literally unbreakable. Yeah, it's like a traffic jam, but for sound waves. All those little warnings that couldn't get out ahead of the plane all get stacked up into one huge, instantaneous change in pressure and density that the plane has to physically punch its way through. Now, we're not talking about just a little bit of extra resistance here. No, this wave drag is an absolutely massive force. The amount of energy the engines have to burn just to keep pushing against this shockwave is incredible. For those first pilots, it literally felt like flying into a brick wall in the sky. And what's so cool about this graph is that it shows you the problem and the solution all at once. That steep red curve, that's the brick wall for a straight-wing plane. But that blue curve, well, that hints at the first brilliant way engineers figured out how to cheat. So how'd they do it? How did they get past that wall of drag? Well, the first big breakthrough was this amazing aerodynamic hack that was as elegant as it was revolutionary. They just angled the wings. You see, by sweeping the wings back, you're basically tricking them. It's so clever. From the wings' point of view, the air isn't hitting it head-on anymore. It's coming at an angle. This simple bit of geometry delays that powerful shockwave from forming, and it lets the plane fly much, much faster before that drag wall really kicks in. And this wasn't some brand new idea. It actually came out of Germany, way back in the 1930s. After World War II, that knowledge got out, and it completely revolutionized the design of high-speed jets for everyone. Okay, so sweeping the wings was a huge deal. But that was just step one. The next leap forward was to stop thinking about just the wings and start thinking about the entire airplane as one single smooth shape. And this is where a guy named Richard Whitcomb, a NASA aerodynamicist, had this total aha moment. He figured out that to beat the shock waves, the plane's total area, if you took a slice of it from nose to tail, had to change as smoothly as possible. No sudden bumps. And that idea led to this really unique, almost iconic look. To make up for the extra area that the wings add, you have to narrow the body of the plane right where the wings are. And what do you get? You get this famous Coke bottle shape. And this wasn't just theory. The area rule literally saved the F-102A fighter program. I mean, the prototype was a dud. It couldn't break the sound barrier. But after they applied Whitcomb's idea, gave it that Coke bottle shape, it became a successful supersonic jet. Amazing! All right, so we've reshaped the whole plane. What's next? Well, now we're going to zoom way in, right to the specific curve of the wing itself. This is called the supercritical airfoil, and it is a masterpiece designed to basically soften the blow of the shockwave before it can cause too much trouble. Just look at the shape here. See that? The top surface is way flatter than a normal wing, and then it has this sharp curve down at the back. That very specific shape is engineered to create a much weaker, much less draggy shockwave. It's just brilliant. And what this brilliant design does is give engineers two incredible choices. They can either fly faster without paying a big drag penalty, or at the same speed, they can use a thicker wing, which means it can be lighter, stronger, and, you guessed it, hold more fuel. It's a win-win. So these incredible innovations totally cracked the code for transonic flight and made supersonic travel possible. But, engineers, they're always asking, what's next? Where do we go from here?
Well, the same basic ideas still matter, but they get a little weirder at really high speeds. For a plane like the Concorde, the shock wave forms a cone behind it, like the wake of a boat. So, to reduce drag, the whole shape of the plane is designed to fit inside that cone, which is why its wings are swept all the way back to the tail. And believe me, the list of tricks goes on and on. It's like a secret toolkit for high-speed flight. We're talking wings as thin as knife blades, tiny little fins called vortex generators that stir up the air. All these little things that add up to a huge advantage in the fight against drag.
When you get right down to it, designing one of these planes isn't just about one part. It's like conducting an orchestra. Every single curve, every single component has to work in perfect harmony with the laws of physics across the entire aircraft. And that right there brings us to the edge of what's possible today. Pushing even faster into hypersonic flight at 5 times the speed of sound or more, well, that means the rules are going to change all over again. It's going to demand a whole new understanding of physics and a new generation of genius solutions. The only question is, what will that next big breakthrough look like?